Hello and welcome to this video where today we're looking at electron microscopes as part of the AQA turning points option. Now these are basically the two things that you need to know. There are two types of electron microscopes. There's the transmission electron microscope, or the TEM, and we need to know what the rough design of this is and basically how it works. And then the second type of microscope is the scanning tunneling microscope, which is a completely different type of microscope, but again we need to know roughly what it's made up of and basically how it works. So this thing here shows you a very rough idea of a transmission electron microscope, and what it really uses is it uses magnetic fields to basically to focus electrons. So each one of these things here is a lens. And if you remember back, if you did, for example, P3 in AQA at GCSE, you remember that if you had a lens that looks like this, so if you had a convex lens and light came along parallel like this, then what it would do is, as it went through the lens, it would all be focused onto one particular point called the focal point, and light rays that went straight through the middle just carried on going on in a straight line. So it looks something like that, and it all focused on one point. If, however, you had the lens like this and the lines were coming from the focal point like this, the light rays like this, then when they got to the lens, what they would do is they would then go in a straight line. And basically this thing works in exactly the same way, apart from now that we've got electrons which are charged, we can use magnetic fields as our lenses instead of obviously using glass, which is what a normal microscope does. So each one of these basically consists of, in here is basically a coil of wire which is connected to a power supply, and it creates a magnetic field. But each one of these coils is contained within basically within like a soft iron container, if you like. And what that does is it keeps the magnetic field inside it. So if we change colour a bit, what the magnetic field looks like around it is basically it goes around the coil like this. Now you might not be able to see, but here there's now a gap in this particular metal casing, and so what happens if we change colour again is that the magnetic field can move out of here. So actually there's a bit of a magnetic field here, and this gap extends all the way around here like this to the other side. And these things would be complete circles. We've just cut it away so you could see it. And what you would see is that the magnetic field basically forms this shape here like this. So you would see there's a magnetic field here. And when the electrons come down here, if they come straight down in a straight line right through the middle of here, they're not deflected at all. Whereas if they came down here, for example, they'd be deflected by the magnetic field and they'd be deflected back towards the middle like this, for example. So this is exactly the same as this situation. And you can imagine that if they all came from a central point, then they'd be deflected again back towards the centre. So if we have, let's say we have a yellow colour, if they were all coming from a central point here, like this, when they got to here, the straight ones would go straight through, these ones would be deflected straight downwards like that. So they work in exactly the same way that these things do, apart from we're working with electrons. So this is the transmission electron microscope. So basically what we have, if we switch back to a colour we can see, we've got an electron gun. So that creates a beam of electrons by, unsurprisingly, thermionic emission. And then once we've got these electrons, basically again we accelerate them through a potential difference, and it's a constant potential difference. So what that should mean is that all of the electrons basically have the same velocity. And if they have the same velocity, then because we know from de Broglie's equation over here, so lambda equals h over mv, they're all electrons, so they have the same mass. They all have the same, or they should all have the same velocity, so they should all have the same wavelength. So these magnetic fields will affect them in basically they'll affect all the electrons in the same way. And when it comes to diffraction, they'll all behave in exactly the same way because they've got the same wavelength. So we basically create these electrons, and these black lines here show you the path that the electrons take if they're, for example, going out from this point. The blue line, the blue dotted line, shows what happens if they basically create a straight down, and obviously there'll be electrons in between these two extremes. So this is basically how your electrons are created. They very first of all go through a condenser lens. And basically what this does is it forces all of the electrons into a parallel beam. Parallel. So that's the first thing that happens. So these electrons are spreading out from this point here, and then when they go through this condenser lens, it forms them all into a parallel beam. So they're all now going in the same direction downwards. And they keep on going, and then what you do is you place your thin sample here. So you put a thin sample of whatever it is that you want to look at here. And it has to be thin because the electrons have to be able to pass through it. If you think about a normal microscope, what you have is you basically have like a stage where you put a slide and potentially a mirror here, and you put your eyepiece here, and what's happening is the light comes along, it reflects off the mirror, it goes through the sample, and then it gets magnified in these lenses, and then basically you see it. So light has to go through a sample in exactly the same way with an electron microscope. Electrons have to go through the sample. So you put your thin sample here. As they go through the thin sample, they basically diffract, and so they get diffracted by the sample. But also on top of that, some of them get absorbed in places where, for example, the sample is very slightly thicker, for example, and so the electrons are kind of like picking up the image. Now, this sample is just before the objective lens, so the electrons come through here. It basically scatters and diffracts the electrons and absorbs some of them, and then what the objective lens does is it basically deflects the scattered electrons like this. So basically what they do is they cross over like that, and then they form what's called the first image here. So you get an actual slightly bigger image of your sample than you did to start off with. So they've crossed over like that, and you've got your first image, but it's still not really big enough to see. So that there is called the first image, and that's simply all what your objective lens does. It basically takes the scattered electrons and basically takes them and spreads them out so you can see them as a first image. But you want to see them bigger than that because you want to see as much detail as you possibly can do. And so they then go through a projector lens. So again, the straight ones go straight through. The ones that are going furthest away get affected by the magnetic fields in this direction. So you've gone from a very small sample here to a slightly bigger image here, and then these get really spread out onto a fluorescent screen. And where the electrons were absorbed, you'll see dark bits, and where they weren't absorbed, you'll see light bits. And so what you really see is an image where on this fluorescent screen, because the electrons hit on here, and you basically see what your sample is made up of. So that's how your electron microscope works. Basically, it works like a normal microscope, but it uses electrons instead. Now, in theory, an electron microscope can resolve down to actually individual atoms. So basically, for that to happen, you'd have to have a wavelength of these electrons to be approximately the same size as an atom, which is somewhere in the region of around about 0.1 nanometers. In other words, roughly 1 times 10 to the minus 10. Now, from that, one of the things you are expected to be able to do is to work out the accelerating potential that these electrons would have to go through in order to obtain a de Broglie wavelength of this big. So what you would do is you'd go back to your wave-particle duality that we looked at in the previous video, and you take this equation here, 2mEVA. So you know what the wavelength is because it needs to be roughly the same size as the object you want to look at, because that size will diffract these things. This is the mass of the electron, that's your charge of your electron, and VA is the accelerating potential. And if you put all of those numbers in and rearrange the thing, then actually you end up with an accelerating potential of roughly 150 volts. So you only have to accelerate these electrons through 150 volts in order to actually, in principle, see individual atoms in your sample here, and then you get it projected and you would see an image of all of the atoms that are on here. Unfortunately, that's what would happen in theory. In principle, that's not quite what happens. So there's a couple of extra little details that we're going to have a look at. So the detail that you see is determined by the resolving power. Okay, so we want to see some detail. So if we actually have if we could zoom right in to a surface, what you'd see is you'd kind of see almost like individual bumps where the atoms were like that, if you could actually see these things. And the detail that we could see, if we could see individual atoms, that's determined by what's called the resolving power. And the resolving power is simply the least separation between objects that you can see apart. So in other words, for example, if you had two atoms like this and you could see them apart, then the resolving power is enough to be able to see those, and you could measure that distance there, and you could say, okay, the resolving power is this much because I can see these particular things here. If, however, the resolving power of your microscope isn't big enough, then what you would see is you'd see one atom there and you'd see another atom there, and you can't distinguish these two things. So that's what it means by resolving power. And the resolving power increases as the wavelength decreases, because basically these things will be diffracted, the electrons will be diffracted by smaller and smaller objects, and which basically means that you'll be able to distinguish between smaller and smaller objects and smaller distances, so the resolving power increases. But in practice, there are two things that kind of get in the way. Sample thickness. You have to put a sample here, basically, because obviously that's what you're looking at, and it has to have a certain thickness associated with it. You can't have a zero thickness. And what happens when you have a thickness of your sample is, as the electrons go through here and scatter and diffract, they slow down. And as we know, the wavelength of these things is equal to h over mv. So if they slow down, basically what's happening is the velocity decreases, so the wavelength increases. If the wavelength increases, then the resolving power decreases as well, so you won't see as much detail as you should do, simply because the electrons are slowing down. There's also something called lens aberrations, and they kind of fall into two categories. The first one of these things is basically because of thermionic emission. So I kind of said before, and I kind of hinted at this, if you've got your thermionic emission and you accelerate all of your electrons through a constant potential difference, then actually they should all have the same speed. But unfortunately, they don't. So there is a slight issue with getting them all to have exactly the same speed. When some of them are emitted from the metal, some of them might have a very small amount of kinetic energy to start with, because they came from the surface of the metal, whereas the electrons that came from the surface of the metal here, they were able to be freed with less energy than ones that were deeper inside the metal, like the photoelectric. In essence, they would need more energy to get out. So although you're providing the same amount of energy to both electrons, this electron will have a smaller kinetic energy than that one will. So they should have the same speed, but they don't. And so actually you end up with very slightly different wavelengths. And if you get different wavelengths, then these magnetic fields here will affect them in slightly different ways. And actually, if they don't have the same speed, then what happens is your image becomes a little bit blurry. The other thing is that these lens aberrations basically apply to the lenses themselves, because what should happen is that no matter where the electrons are on here, they should all be essentially focused in the same way. However, that doesn't happen. So in practice, what happens is electrons that come from the same point are not always focused in the same way. So if they come from the same point, they're not always focused in the same way. So they're not necessarily focused in the same way like that. And what this means is that actually this electron, all of these electrons on this side should come down this path here, but because there are very slight fluctuations in the current that's in here, the magnetic field, there are very small changes in the magnetic field around here, but it does affect it. So rather than them all coming down exactly down this path here from here, they'll potentially spread out a little bit, and when they do, again, what you end up is with a blurred image. So electron microscopes are incredibly good, and they can in principle see down to the scales of individual atoms. However, in practice that's not true, simply because of these reasons over here. If you do want to see individual atoms, however, you can use this electron microscope. So you can use a scanning tunneling microscope. Now the theory behind this is actually really quite a little bit tricky, but actually in practice it's not really that bad, really. So what we've got here is we've imagined we've zoomed in. This is our sample. So this is a sample that we want to kind of map. And what we're going to do is we're actually going to map the surface of these to build up an image. And this is a really fine tip. It's so fine that it's virtually got one atom right on the end of it. And this is connected to a few different things. So it's connected to something called Piezoelectric materials. And basically what they do is if you pass a current through them, then they change shape. If you've seen old-fashioned kind of like electric lighters, they use piezoelectric materials, but they just do the opposite. What you do is you squeeze the material and it causes an electric current. But you can do the opposite way around. If you actually put an electric current through them, you can make these materials change shape. And we'll see why that's important in a second. It's also connected to a source of potential difference, and what we do is we make this tip negative compared to this. So basically there's a potential difference between these two things. Now what we do is we basically take this tip here and we put it incredibly close to here. So we basically put it in the region of round about 1 nanometer from the surface of the material that we're looking at. And in theory, if we just did that, nothing should happen. But actually, there's a very strange effect called quantum tunneling. So we'll have a quick look at that first. So let's imagine that we've got an electron on this side here, and it's in this first excited state here. It can only, if we give it enough energy, it can get up to the second excited state, but it can't get any higher. So if we put something in the way like this, so this is often called a potential barrier. But it's basically what it is. It's in the way. If we give the electron enough energy to get from there to there, it doesn't have enough energy to kind of go over the top onto the other side. So the electron, in theory, should be contained on this side over here. But because the electrons are waves, and we kind of think of this as a probability wave, which is a very strange concept. But because it's a wave, what it can do is when it gets to here, the amplitude of the wave decreases as you go further through this barrier, but it doesn't ever go down to zero. And so when you get to the opposite side, there is a very small amplitude on this side. But because this is a probability wave, if you've got an amplitude on this side, there is a small probability that you'll find the electron on this side over here. So actually what the electron can do is instead of it's almost like, if you think about it, this is like a hill. It's almost like instead of going over the hill, by going up over the hill and using energy to get to the top and then going back down the other side, instead all it does is take a shortcut and just go straight through the middle. And this effect for one particular electron, the probability of this happening is actually fairly small. But if you load up your tip with lots of electrons by making it negative, if you've got lots and lots of electrons, even though the probability is very small, there is a chance that they can basically move across here. And so they tunnel across this gap, because here there's basically a gap and they shouldn't be able to get across. And so what you do is you basically create a very small current between the tip and here because of this quantum tunneling effect. Now, if we made this barrier thinner, then the amplitude of this wave wouldn't go down as much, and so you'd end up with a bigger amplitude wave, something for example like that. So now there's a greater probability that the electron is going to be on this side. And so therefore what really happens is if you make this gap smaller, so if you took this and you moved this whole tip closer like that, then the gap's smaller, and so it's more likely that electrons go across. So basically let's do that. So if you close your gap, then the current actually increases. The current goes up like that. And obviously if you decrease the gap, the current goes down. So there are two ways that you can use this particular microscope. What you can do is, the very first way you can do that is what we've got here is we've got a surface here, we've got a layer of atoms, and we've got our sample that's put on it. And what we could do is we could move this along at a constant height. If I can try my best to do that. So we move it along at a constant height. So that's the first thing that we can do. So we can keep this constant. It's like that. So we're moving it across at a constant height. Now here, because the distance is staying the same, then you'll have between here and here, as you move your tip, across here, then the current will be constant. But then, as you then move the tip further along, like this, you're keeping this at a constant height, you're not moving it, but basically what you're doing is now, because the sample is closer, you've kept this going along here, but the sample's closer, so therefore the current between here and here, so here, your current is going to go up. And then when you go past this sample, the current goes back down again. So what you can do is, what you do therefore, is you measure the really small tunneling current, and you know that if the current is small, then the distance is big, and you know if the current is big, then the distance is small. And what you then do is you then use a computer, and what that will tell you is it will show you that there's basically something like that, and then it gets bigger like that, and then it gets smaller like that. So you can build up a picture of what this surface looks like. Now this is just a two-dimensional picture. Actually what happens is if you look for this sample from above like this, and your sample is in the middle like this, what your microscope does is it starts off over here, and it basically works across in two dimensions. It'll go down here, up a bit, down here, up a bit, and it'll scan all the way across here, which is why this thing is called a scanning tunneling microscope. So in the end, it scanned its way across all of the sample. So that's one way that you can actually build up a picture of this. There is another way, and that way is basically by keeping a constant current. So that will be, so that's slightly different. So in this case, what we're going to do is we're going to keep a constant current. And for that, if we think about it, to keep the current constant, as this thing moves along here, and it stays roughly the same height, so it'll go up a bit and down a bit, and up a bit and down a bit, and up a bit, and then when it gets to here, to keep the current constant, the tip will have to move up a bit like that, because if it stayed where it was down here, the current would be bigger. So your tip of this probes had to move up, and then it would move back down like that, and it would be able to build up a picture. The problem is that what we need to do is be able to move these things over really small distances. So that's where these piezoelectric things come in. So basically what you do is you feed this current back through these piezoelectric materials, and the current makes those change shape, and when it changes shape, it moves the tip up and down a little bit. So again, what we would do is we would keep the current the same. It would move up and down a little bit like that. And what you do is in this case is you measure basically how much the tip moves up and down, but the process is the same. You take your sample, you scan across it like this, you measure the current, and then you move this thing up and down basically to keep the current constant. So that was electron microscopes in a very quick nutshell. You need to know how both of these things work. You don't really have to be able to explain the tunneling part in lots of detail, but you have to be able to explain how it is that this thing actually works. And for this one, you need to know quite a lot more detail. So you have to know basically how it works, how you use the magnetic fields to focus your electron beams, and finally the drawbacks with this particular one. So that was electron microscopes for AQA turning points. Thank you very much for watching. I'll see you again soon.